Hello everyone. Today we're going to talk about section 2.1, which is about graphs. So in math, graphs are really important, mostly just because you can display and portray data in a easier way to interpret and understand in a way that almost looks like a picture. And graphs are used in so many different fields like business and health and social sciences. So it's a really important and useful tool to have in your belt, and also to know when to interpret them and how to interpret them. So typically when we have graphs, and we have this picture here, which is figure 2.1 in your book if you want to go back and look at it at any point. And basically what we're looking at, it's called a plane. So the graph itself would be a line or a squiggly point or a parabola, which we'll learn about. And so those are what the graphs are. But the plane is the actual thing that we're looking at here in figure 2.1. And the plane that we're looking at, we call them Cartesian coordinate systems. And the most important thing to look at here is that we have a horizontal axis, which is called the x-axis. So we're going to highlight it here. So this x-axis here is the horizontal line. And then we also have a vertical axis, which will be the y-axis. So this axis here. Okay. So we have these, and the point where they meet is called the origin. So we're going to highlight that, and that's called the origin. And that's what they meet. So the origin is the point 0, 0. And those correspond to the x and the y coordinates, which means that the x coordinate is 0 and the y coordinate is 0. And now we see that all these points on the plane, so we see here we have a -2, 4, a 0, 3, 3, 2, 1, 0, 2, -2, 0, -4, and -3, -4. All of these points are called ordered pairs. They're a pair of points. So the pair would be the x coordinate and the y coordinate. And that's how you would always write it. It's always the x coordinate and then the y coordinate. And each one of these points belongs to a quadrant. So if we're looking at this picture, and we see that quadrant 1 is in the top right-hand corner. So we see this is quadrant 1. And then when we count our quadrants, because it's going to be 4 quadrants, and when we count them, we're going to go counterclockwise. So we have quadrant 1 in the top right-hand corner. Then in our top left, we have quadrant 2. Below that, we have quadrant 3, so the bottom left. And then we have the bottom right, which is quadrant 4. So now we have all of these quadrants, and all of our ordered pairs belong to each one of these quadrants, except for the points that are on an axis. So we see here we have points 0, 3, and 0, -4, and 1, 0, and also -5, 0. So each one of those points does not belong to a quadrant since it's on the axis. It's neither in, for example, the point 0, 3 is not in quadrant 1 or quadrant 2. It's just on the axis. So those points wouldn't belong to a quadrant, but they're still points nonetheless. So I'm going to write these out. So we have our horizontal axis is our x-axis. Our vertical, sorry if my writing is not super great on my tablet. Our vertical axis is our y-axis. Then we have our quadrants, So remember that's quadrant 1, quadrant 2, and you'll see that they're often depicted in Roman numerals. You could write them however you like. Quadrant 3 and quadrant 4. And like we said before, quadrant 1 will be in the top right. Quadrant 2 is the top left. Quadrant 3 is the bottom left. And quadrant 4 is the bottom right. Put a little note. In order, begin from top right quadrant. Then go counterclockwise. Okay. So now we've seen here in our figure 2 how our plane is split up and how we would have our ordered pairs. So now that we've had our introduction here, we're going to move on to our next part, which will be equations. So these sections coordinate with the sections in your book. So these are the same sections that you'll see in your book. So if you ever want a reference at any point, you can always go back into the book and take a look at these sections as well. So we have equations, and kind of how I want us to keep this in mind. Sorry if I'm jumping around a lot in here. Is that a solution of an equation in two variables and then we're going to say i.e. or an example, y is equal to negative 2x plus 3. So our two variables in this case would be y and x. So a solution of an equation in two variables is an ordered pair. Numbers. Such that the substitution of the first number for x and second number for y produces a true statement. All right. And basically what this means is that any solution of an equation that has two variables, like the x and y that we saw, is that if you plug in a number for x and then a number for y, if you're given both, and if they both produce the same number, then you have a true statement, and that would be considered a solution. So let's do an example. I'm going to use different color here. So let's do red now for our first example. So we have, oh gosh, that's so small. Okay, so we have our first example here. And this example is actually going to be checkpoint 2 in your book, if you ever want to go look at it. And what we have here is we have y is equal to x squared plus 5x minus 3. And we want to know if any of these 3 ordered pairs are a solution. So our first ordered pair will be 1, 3. Our second will be -2, -3. And our third here will be -1, -7. All right, so if we start with A here, we have 1, 3. So this ordered pair means that our x coordinate is 1 and our y coordinate is 3. So when we plug this in to see if it's a true statement, we're going to plug in 3 for y and 1 for x. So if we do that, we're going to have 3 is equal to 1 squared plus 5 times 1 minus 3. So now we can solve our right-hand side here since it is still expanded. So we'll have 3 is equal to 1 squared, which is just 1, plus 5 times 1, which is just 5, minus 3. And we can simplify more. We have 3 is equal to 1 plus 5 is 6, minus 3. So we end up with 3 is equal to 3. So put a check, and that is a true statement. Since when we plugged in our given x coordinate and our given y coordinate, they came up with the same answer that we had 3 is equal to 3, which means that the ordered pair 1, 3 is a solution. So now we want to see if the others are solutions as well. So now we can do B, which was -2, -3. So our x coordinate is -2, and our y coordinate is 3. All right, so now just like in part A, we're going to do the same thing by just plugging in these values. So we're going to get -3 is equal to x squared, which will be -2 squared, plus 5 times x, which will be -2, minus 3. So we have a little bit more simplification that we'll need to do. And we have -3 is equal to -2 squared, which is just going to be 4, plus 5 times -2, which is -10, minus 3. We can simplify a little bit more. So we have 4 plus -10, which is going to be -6, minus 3. And -6 minus 3 is going to be -9. So take blue here. So 3 and 9 do not match. Or -3 and -9 do not match. So that means that our ordered pair of -2, -3 is not a solution. So far we have 1, ordered pair 1, 3, which is a solution, and one ordered pair -2, -3 that is not a solution. Now we want to try out C, which is -1 and -7. So our x coordinate is -1, and our y coordinate is -7. All right. Kind of losing it, so let's do that. Okay. So we want to set it up just like we did before. So we have -7 is equal to -1 squared plus 5 times -1 minus 3. So we simplify this, and -1 squared is going to be 1 plus 5 times -1 is going to be -5 minus 3. So we have -7 is equal to 1 plus -5, which is going to be -4 minus 3, which will give us -7 is equal to -7. So we have that solutions of our equation will be ordered pairs of 1, 3, and -1, -7, and not -2, -3. So by doing this, we have found two solutions of our equation. So now that we've done that, we can take some notes on equations in general. So equations, it's a Q. Equations that are like this typically have an infinite number of solutions. So in order to find one, the easiest way would be to pick a value of x. So you can pick any number of x, and then compute y from your given equation. So this way, if you're given an equation and you want to find just any solution, you can just pick any number of x and then just compute y. Or the other way around, you can choose a value of y and just compute a value of x. So like in the one that we just did, so an example, we just had y is equal to x squared plus 5x minus 3. And let's say I want to find a solution where x is equal to 2. So I'm going to pick x equals to 2. And now I'm going to compute y. So I get y is equal to 2 squared plus 5 times 2 minus 3. So we get y is equal to 2 squared, which is 4, plus 5 times 2, which is 10, minus 3. So we get 14 minus 3. So we get that y is equal to 11. So we'll say a solution is 11. So now we found another solution in addition to the solutions that we found from our last example. So now we have an extra solution. So, given this information, we can say that the graph of an equation, because remember we said in the very beginning that a graph is actually the image of the equation and the plane is the actual graph, or the plotting that you see there. So our graph of an equation is the set of points in the plane that are solutions to the equation. So, an important point, so I'm gonna put it in this purple color. The important point here is that this makes a graph a picture of the solutions to an equation. And in addition to that, since there is typically an infinite number of solutions, our graphs will normally be infinite. And by saying that our graphs will normally be infinite, this is just a way to explain that when we see a typical graph, maybe something like this, and we go ahead and maybe we graph a line, something looks like that, we see that they'll go on forever since they're lines and they have those arrows. So they go forever in either direction. So that means that the graphs themselves are also infinite since there are an infinite number of solutions. All right. So now we can go ahead and talk about our x and y intercepts. So an x-intercept is essentially the x coordinate of the point of the graph that crosses the x-axis. So this means that if we draw another example graph here, and we would kind of stick with what we had last time. We had to kind of do that like that. If our x-intercept is where our graph crosses the x-axis, then this means that that point would be right here. This point would be our x-intercept. And since this point is crossing the x-axis, this means at this point, our x-coordinate is going to be some number, and our y-coordinate will be 0. So we get that our x-coordinate will be a number, and our y-coordinate will be 0. So to find an intercept, in this case an x-intercept, so to find an intercept algebraically, I don't know if I spelled that right. Algebraically is the word I'm trying to say. To find an intercept algebraically, all you need to do is set one variable to 0 and solve for the other when given an equation. Okay, so now to say the same thing about a y-intercept. So a y-intercept is essentially the y-coordinate of the, what is that equation? The point. Of the point graph that crosses the y-axis. So an x-intercept crosses the x-axis and the y-intercept crosses the y-axis. And everything is pretty much the same, just now you would switch x and y as we did before. So we would also say that the y-coordinate will be a number and the x-coordinate will be 0. So for an example, you would have points that look like 0, 5, or 0, negative 10, something along those lines. And then similarly for an x-intercept, we would have 5, 0, or negative 10, 0. And it's the same thing to find the intercept algebraically, is that you would set your, in order to find a y-intercept, you would just set x equal to 0, and then you would solve for y. And then to find an x-intercept, you would set y equal to 0, and you would solve for x. So let's do another example. And this example is number 20 in your book. Number 20 being in the back of the section, there's going to be a long list of problems, so this is number 20 from that section. So we want to find the x and y intercepts and sketch the graph of 3x plus y is equal to 4. So our equation here is in a little bit different of a form than how we've seen it before. Now it's 3x plus y is equal to 4, whereas before we would have y would be equal to some number times x, and then maybe plus or minus another number. So all we have to do is just rearrange this to get it in the form that we want. So we can just rearrange to get, we had 3x plus y is equal to 4. So let's subtract 3x from both sides. To get y is equal to negative 3x plus 4. So this is what we're going to use instead. All right. So we have y is equal to negative 3x plus 4, and we want to find our x-intercept and our y-intercept. So we can start with our x-intercept. I'm going to write x-int just as an abbreviation. And so what we want to do, remember, is to set y equal to 0 and then solve for our x. So if we do that, we're going to get 0 is equal to negative 3x plus 4. So now we just want to solve. So let's subtract 4 from both sides. And we get negative 4 is equal to negative 3x. So now let's divide by negative 3. And we get x is equal to negative 4 divided by negative 3. Since they're both negative, they both become positive. And we get x is equal to 4 divided by 3. So that is going to be our x-intercept. Now we want to find our y-intercept. And we can actually rewrite this. So since our x-intercept is 4 through the x-coordinate of our x-intercept is going to be 4, 3. So that means that that point is going to be 4/3, 0. Now, for our y-intercept, we're going to have our y be what we're going to solve for, and then we're going to set x equal to 0. So we're going to get y is equal to negative 3 times 0 plus 4. That just simplifies to y equals 0 plus 4. So y equals 4. That will be the y-coordinate of the y-intercept. So we would say or 0, 4. So now we have our intercepts. And now we want to graph. So if we do that, then first thing we want to do is set up a table just so we have a good range of values that we're going to test. So let's see the blue. So we're going to set up a table here. And let's start with a few negative numbers, and then we'll have 0, and then we'll have a few positive numbers, just so we get a good range. So let's just start with negative 2. Then we'll have negative 1, and then 0, 1, and 2. So now we want to find our y values by plugging our x values into our equation. So if we want to solve for negative 2, we'll say y is equal to, our equation was negative 3 times x plus 4. So y is equal to negative 3 times negative 2 plus 4. So that will be equal to negative 3 times negative 2 will be 6 plus 4, which is equal to 10. So we have that value is 10. Now we want to do for negative 1. So we'll say y is equal to negative 3 times negative 1 plus 4. Negative 3 times negative 1 is going to be 3 plus 4. And we're going to get 7. So that's going to be our y coordinate. Then we have 0, which is coincidentally going to be our y-intercept, which we already solved for earlier over here. So if we set x equal to 0, we know our answer will be 4. And this is our y-intercept. Now we can plug in 1, so we get y is equal to negative 3 times 1 plus 4. That will be negative 3 plus 4, and our answer will be 1. Then lastly, we want to do 2, so we'll get y is equal to negative 3 times 2 plus 4, which will give us negative 3 times 2 is negative 6, and plus 4. So this will be negative 2. All right, so now we have a few ordered pairs here. So let's make a list. Our ordered pairs will be negative 2, 10, negative 1, 7, 0, 4, 1, 1, and 2, negative 2. And now we want to establish our graph. So start up here. And we see here that we have a very small negative number, but a pretty high positive number as far as the y-axis goes. So we're going to have our x-axis be a little bit towards the bottom. It's not going to be totally even. Like that. And then we can label, so we make our notch marks here to represent our values. This will be 1, 2, 3, 4, and so on. 5, 6, 7, 8. Oh, I was so close. Okay, let me extend this a little bit more. So that's 8, 9, 10, 11. There we go. And we're going to have a couple notches here and here as well. So this will be 1, 2, 3, 4, 5, 7, 8, 9, 10. And we'll put in that. And then these will be negatives. This will be negative 1, negative 2, negative 3. This will be, we'll get a little small here, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. All right, so now we have our plot or our plane, and we have labeled everything. So now we can plug in our ordered pairs and our intercepts. So let's begin with our intercepts. So our intercepts will be in yellow, and we know that our y-intercept is at 0, 4. So we start here at our horizontal axis or our x-axis, and we know that it's 0, so we'll start at the origin. and then we'll go up 4. So 1, 2, 3, 4. Now for our x-axis, a little trickier. It's going to be 4 divided by 3, 0. So we start at the origin, and since that is our x-coordinate, we're going to go on our x-axis, and we're going to go to the right since it's positive. And we know that 4 divided by 3 is technically 1 1/3, so we know it's a little bit greater than 1. And since we're not drawing perfectly to scale in this case, I'm just going to make it a little bit greater than 1. So I'm going to put it right there. Now, let's put in our ordered pairs. So our first ordered pair would be -2, 10. So we'll go start at the origin. We'll go 2 to the left, -2, and then we're going to go up to 10, and we'll make a point. And that will be -2, 10. And our next one is going to be -1, 7. So we're going to start at the origin. We'll go to the left 1, so -1, and then we're going to go up to 7. And it looks like 7's kind of on that spot, so it's going to get a little covered up. Sorry about that, 7. And we're going to label that, put a little line so it doesn't get too cramped. That's a -1, 7. Then we have 0, 4, which we already marked because it was our y-intercept. Now we're going to go 1, 1. So we'll go start at the origin, and we'll go to the right 1 spot, and then we'll go up 1 spot. And that will be 1, 1. And then we have 2, -2. So we're going to go to the right 2 spaces. So that will be +2 on the x-axis. And then we're going to go down -2. And that will be -2 on the y-axis. Oh, forgot to label this one. This was 1, 1, 1. And this one's going to be 2, -2. And can't forget to label these, the y-intercept and the x-intercept. So now we want to connect these dots, go through our y. Oh, sorry, I'm like so squiggly, not straight. Okay, not quite that straight, but you get the point. You want to connect all of your ordered pairs, go through your y-intercept and your x-intercept. And so now, and then we want to draw our arrows to signify that this graph will be going, and it's going to go through that, be going on infinitely. So they're going to go on infinitely in either direction. So now what we have here with this graph is we have a picture of all the solutions of our equation. All right. So now we can go on and we have here our new section. Graph reading. Oh man, draw a G. There we go. So now I have graph reading. And again, just to start off with, an important phrase to keep in mind is that information is often displayed in graphical form so it is important to be able to read and interpret graphs. And this was something I kind of mentioned in the very beginning. So a lot of the times, a lot of like companies and hospitals and many other corporations will collect all of this data, and then the way that they display it is within a graph, because it's really annoying to read like giant long data tables and everything. And so a really simple way is to put it in a graph, and then it's a lot easier to read, and you kind of get this whole picture of what's kind of going on. So for graph rating, it's important to just look at examples. So we're going to have another example, and we'll pick green. So example 3, which is going to be actually example 5 in your book. And I saved an image up here before we started, so I'm going to grab it and bring it down. Ooh. So I make this a little bit bigger. So our example here is that finance newspapers and websites summarize activity of the S&P 500 index in graphical form. The results for the 20 trading days for the month of December 2012 are displayed in figure 2.7. So that's 2.7 that we're looking at. The first coordinate of each point on the graph is the trading day in December, and the second coordinate represents the closing price of the S&P 500 on that day. And the data is from www.morningstar.com if you ever wanted to check. So our questions here that we want to know, part A, is what was the value of the S&P 500 index on, that's 2 words, on day 11 and day 17. So if we want to find the value of the S&P 500 index on day 11 and day 17, we want to look at this graph. So days we see is our x-axis. So day is our x-axis here. So we can label that x-axis. And our S&P 500 index value is our y-axis. Oh, that was supposed to be cool. All right, so if we're looking at these, then we want to start with day 11 and day 17 to find our value. So we start with day 11, and we find, and let's kind of zoom in here on our graph. So we start at day 11, which looks like right here. And what we want to do is find the value, and the value is going to coordinate with our y-axis, or our y-coordinate. So if we start at 11, all we want to do is track upwards until we hit the point where we touch our graph. So it looks like we hit right here, and then we can track back towards the y-axis to find that value. And it looks like that value is 1,430. So let's write that in. So we say on day 11, the value was 1,430. And now we want to check for day 17. So looks like Day 17 is going to be right here. This is 17. And then we want to do the same thing. So we're going to track upwards until we touch our graph. So right there. And then we want to track to the left to our y-axis, which we see is at 1,420. So on day 17, the value was 1,420. We want to write these as ordered pairs. So in ordered pair form, say we get oh my gosh, 11, 1,430, and 17, 1,420. And that's because on day 11, our value of our S&P 500 index was 1,430. On day 17, our value of our S&P 500 index was 1,420. So that means that our first ordered pair will be 11, 1,430, and our second ordered pair will be 17, 1,420. So now, part B, what we want to find is on what days was the value of the S&P 500 index above 1,425. So if we want to find the days where the value is above a certain number, then we're going to go back to our graph here and zoom in a little bit. And what we're going to do is we're essentially going to make a cutoff. Or in our case, they already filled in the cutoff, but let's highlight it here. So our cutoff, which was 1,425, which we see is this kind of purple line here on this graph, or on this plane. So let's highlight that. And that would be our cutoff. So now what we're looking for is basically every point where we see above that line. So it looks like our very first point here will be this point right here, which we see if we track down, we'll see our x coordinate is 5 and our y coordinate is, oh, we just need to know it's above 1,425, so we don't actually have to know the y value, we just have to know that it is above. So we know that this is 5, and it looks like our, that is 7, it's between 6 and 8, so it's 7. And our next value, which is 8, then it looks like 9 is below and 10 is below, but 11 is definitely above, and it looks like 12 is definitely above. Same with 13 and 14, 15 and 16, but not 17, not 18, not 19, but 20, just barely. So we've now found where all of our days are above the value of 1,425. So now all we have to do is write them down. So we know that on days 7, 8, 11, 12, 13, 14, 15, 16, and 20. Those values were above 1,425. Therefore, those are our days, which are coordinating to our x coordinates of those points. So there is another section in your book, and it's called Technology and Graphs. And basically what it goes over is how to graph things in a graphing calculator and how to utilize certain functions in a graphing calculator. So if you have a graphing calculator and you would like to know those, then please feel free to go through that section if you would like. A graphing calculator or a scientific calculator is required for the class, so you don't have to have a graphing calculator, but if you do, then you can feel free to go through that section as well. Then our last section here is, or not a section, it's just an example. We're going to do one last example, which will be, pick a color. Let's do this navy blue color. So we'll do example 4. And this is going to be example 8 in your book. So what this example wants us to do is we want to find the roots of x cubed minus 5x plus 1 is equal to 0. So in this case, we see that our y coordinate or y value is set to 0. So this means that what we're looking for is our x coordinate. Or in this case, we're going to have multiple x intercepts. So we want to find these x coordinates of our x intercepts. So if you have a graphing calculator, you can definitely enter this in into your graphing calculator and see how it's graphed, and you can find what's called the root finder, which is just an action in your graphing calculator. Or what you can do, which I think is a really helpful tool for students, is you can use Desmos. I'm going to flip my laptop here. So I'm going to share another screen here. And there's my Zoom. But this is what Desmos is. So it's basically just an online graphing calculator. But it is super helpful, and you can also find roots in this case as well. So we're just going to use the example that we had, which was x cubed minus 5x plus 1 is equal to 0. Ooh, ooh. Whoa, oh my gosh. That's crazy. Maybe we set it equal to y. There we go. Set it equal to y, don't set it equal to 0. I think I may have read that wrong. But, so we see here that we have this graph, and we can zoom in and out. You can just scroll if you have a mouse, or they have the toggle windows so you can zoom in and out. And we see here that we have 3 x-intercepts. And if we want to find the roots, all the root means is the x-intercept, essentially. It's just the x-coordinate of the x-intercept. So you can just click on that spot, and it will tell you. So for this x-intercept, we have negative 2.330. For this point, we have 0.2020. And for this point, we have 2.1280. And if we, for fun, we can look and see that our y-intercept is at 0, 1. And there's only one y-intercept, but there can be multiple x-intercepts. And so we see here we have 3 x-intercepts, and these would be considered our roots. So if you have a graphing calculator and you use Root Finder, it will just automatically find these roots for you. But if not, you can always go into Desmos and you can graph anything you want. You can set up tables. If you look here in the little plus button, you can go there and you put in expressions, notes, a table, a folder, image if you'd like. If you put in a table, it will plot all those points for you. And then you can kind of like toggle around with different values of things. Like if, for example, if we wanted to put in maybe A, you can add a slider of A, so you can play with different values of A and see how your graph kind of ends up looking kind of crazy. But those are some things that you can do with Desmos. So Desmos is a really helpful tool that you can use anytime in this class, and it's super helpful. So please, by all means, use Desmos. And let's get back to our notes here. And we just fill in our answers. So we found the roots, which were, can I get my laptop down again? So we found our roots were negative 2.330, 0.2020, and 2.1820. So those were our roots, which we found through Desmos. All right. So that concludes my lecture with section 2.1. Tomorrow we'll be going over 2.2, which is more about equations. And then on a review day before our next test, which is going to be on Thursday. So don't forget, and I will remind you, it's Good Friday. I will remind you about it. And so we will do more problems from the back of the book, and we can just review this section again then. So don't forget to use the online question form if you have any questions at all. And please do not hesitate to email me if you have any questions, and please, you can drop into my office hours whenever you'd like, and ask me anything then. So I will see you guys later. Thanks for listening.